So in order to find a potential function for a vector field, we're going to have a lot of steps that are on the screen, and it might look kind of intimidating, but we're just going to go through it one at a time. So this is going to be something we do when we're given a vector field f equal to ABC, where a, b, and c can be functions. And then we want to check if there's some f so that capital F is equal to grad little f, where grad little f we know is df dx, df dy, and df dz. And the challenge here is that we don't know what little f is. We're only given capital F, and we want to know, is there any potential little f that would give us capital F in this equation? Taking it component by component, if the vector field f is equal to ABC, and it's also equal to df dx, df dy, df dz, then we have a system of three equations. We know that df dx has to be equal to A, so the first components agree. Then for the second components to agree, we know that df dy has to be equal to B. And for the third components to agree, we need df dz equal to C. So this might feel kind of familiar to when we were solving like critical point problems, finding maxima and minima. We started with the gradient, set it equal to something, and we were trying to solve based on those three equations. But in this case, we're trying to solve for f, which makes it a little bit more complicated. So what we want to do is we want to rearrange all our equations in order to solve for f. And the way we're going to do that is we're going to integrate. So we're going to use integration to solve this problem. Oh, I already put the colon there. I just gave myself way too much room to write. Okay, so if we integrate both sides of these three equations, what we get is that from the first one, f should be equal to the integral of a with respect to x. And then I'm going to go ahead and fill in that there's also this k1 of yz that I'll sort of describe more what that means later, but it's a constant that comes out of your integral. If we look at the second equation, df dy equal to b, and we sort of integrate, we would get f on the left side, we would undo that derivative, and then on the right side we would get that f needs to be equal to b integrated with respect to y. And there might be an unknown constant in there that we're going to call k2, and that might be a function of x and z. And then also, if we looked at the third equation and integrated both sides, integrating the left again would just get us f, we undo the derivative, but integrating the right would give us the integral of c with respect to z, and then out of that integral we might have some unknown constant k3, which is a function of x and y. And so this K1, K2, and K3 is usually what throws students off in this section. And those are really just unknown constants. Sort of the same way you have plus C when you integrate with respect to one variable. Oops. I want to center that more. But since we have this input yz, xz, and xy, those are actually going to be functions. And the reason for that is because you might remember every time we take partial derivatives, we might say something like, when we took this partial and got 0 out of it, it was because x is a constant as far as z is concerned. And so when we're integrating with respect to only one variable, for example here integrating with respect to x, anything that depends on y and z is a constant, but it's also a function if you think about y and z as their own variables. I know that's a little complicated. I promise it'll get more concrete as we work on an example, but let's just go through the rest of the steps so we have an outline for what to do. So after you get these equations that tell you how you would solve for f if only you knew what those unknown constants are, what you're going to do is you're going to calculate all of the integrals in those equations, and you're just going to ignore that k1, k2, and k3 that showed up previously. And then once you integrate these three integrals right here, what you're going to do is sort of start to compare their outputs. So you're going to take however you evaluate a dx and leave it as it is. And then you're going to move forward and you're going to look at the second integral, integral of b dy. And what you're going to do is you're just going to cross out any terms that match what you found in a dx. And then you'll go down the line, you'll look at your third integral that you could possibly calculate, integral of c dz. And after you calculate that integral, you're going to cross out any part that matches what you got from a dx or the integral of b dy. And then once you've done that for the three different integrals, you're going to take f and you're going to make it the sum of everything you found in parts 4, 5, and 6. And the only reason this isn't a flat sum of these three integrals is because what we're going to do is we're going to leave off any of those terms that we crossed out in steps 4, 5, and 6. And then I wrote this, you go in the order X, Y, Z, but that's not a fixed rule. You can go ahead and change the order of variables that you choose to integrate when you're going in steps 4 through 6. So that's how we're going to solve this type of problem, and we'll do an example in just a second. But I just want to make sort of one important note. So if you recall back to when we learned gradients, gradients are a way that we calculate derivatives in 3 space. So if capital F is a gradient, and then little f is something we solve by sort of integrating f, we can think about f as being the antiderivative of the vector field f. So a gradient, grad f, which would give you a vector field like capital F, is a derivative. But if that's true, then the little f that you get out of this integration process and the little f that you would have calculated a gradient from, that's going to be an antiderivative to the capital F. So all we're doing is we're kind of like closing the loop of we learned how to turn functions into vectors that represent derivatives, and now we're learning how to take functions that are derivatives and turn them back into an antiderivative.